on observational
Recording in
signatures
progress.
of heavy element nucleosynthesis.
Okay, hello everyone. First of all, you can see this screen. Oh, oops, I'm already advancing. That's not great. You can see my slides, right? I'm assuming you all can. Okay.
Yes, we can.
All right, great. Thank you. So again, thank you for tuning in. Thank you for the invitation to speak at this meeting. My name is Erika Holmbeck. I am currently a postdoc here at RIT. For those unfamiliar with what I do, I study the production of the heaviest elements in astrophysical sites like neutron star mergers. I do this both with theory and observation. On the theoretical side, I also run a lot of these nucleosynthesis simulations like what Jonas was showing. I use a different reaction network, but they accomplish the same thing pretty much. But today I will be discussing the observational signatures that can be used to study heavy element production. Okay, so with those observational signatures, say a merger event happens on the order of seconds to days and possibly weeks, we can get these direct observables like the gamma ray burst, the gravitational waves, of course, and in the best case scenario, like GW170817, the kilonova signature. And we've heard a lot about how important these are, and we will continue to hear more about kilonovae tomorrow. Yeah, they're just really great for studying all of these questions. And it goes without saying that to call these observables, these direct observables, important is a massive understatement. These direct observables are invaluable for studying some of these questions. I've listed a couple here. I know there's way more physics that can be learned from these. I just didn't have a lot of space in this little box, so I apologize if I left out your favorite implication here. But I'm going to disappoint all of you, and I'm not going to talk about any of that stuff. I'm here to talk about the indirect observables that are left over from potential merger events that happened on the order of millions to billions of years ago. So these indirect observables happen on much longer timescales after the merger event. And these are going to be especially useful when we're still in the realm of small number statistics on these direct observables, especially things like kilonovae. As you will see when I define what these are, they are a little bit more frequent, so we can use more of them. And then maybe we can study these things as well. Okay, so back to the other half of my talk title. That indirect signature has to do with the synthesis of heavy elements in merger events. And of course, by heavy element nucleosynthesis, I do mean the R process, nucleosynthesis by rapid neutron capture. A big thank you to Jonas for giving that great summary of the R process in the previous talk. It makes my job a lot easier, this talk a lot shorter, which means we can all refill our coffee a lot sooner. So as Jonas explained, this involves a ton of neutrons. If you were paying attention to the time on that Skynet video, the time it takes to get up to the heaviest elements was a second. And then after that time, all these unstable isotopes decay into this very characteristic abundance pattern where you get these peaks corresponding to these nuclear closed shells. And again, as Jonas pointed out, this pattern created by the R process is distinct from other ways in which the elements are produced, notably distinct from slow neutron capture. So for evidence that the R process occurs at all in the universe, we need to look no further than our solar system, really no further than Earth. So this plot, again, this is a little bit of, this is repetitive with what Jonas said, but this plot shows the abundances of the heaviest isotopes in the solar system in gray. If you run a simulation for slow neutron capture, the physics of which are pretty well known since that stays pretty close to stability, or it is stability. These are the abundances you get for slow neutron capture. Now it's pretty clear that slow neutron capture can't explain many of the isotopes. About half of these heavy isotopes in the solar system can't come from just slow neutron capture. And of course, the other half is what we call the R process component to the solar system abundances. So whenever I say solar R or R process component, to the solar system. I'm talking about this pink line in particular. So again, just by looking at this pattern, and especially things like thorium and uranium, which can only be made by the R process, this is proof that this R process has occurred astrophysically. It's occurred somewhere in the universe. And this signature allows us to study the R process, and therefore whatever astrophysical events undergo this process, like neutron star mergers. The hiccup with using solar system abundances to study the R process and to study specific sites is that we can't know for sure that all of these abundances, this whole pink contribution, whether that came from one specific site, let alone just one event in particular. And that's because the sun is quite young. It was made out of gas. It had been polluted by many generations of stellar evolution. It just has a lot of history in it. So we don't know where these elements came from. We can't be confident about how many, what I like to refer to as chemical ancestors the sun has. But still, it's technically some of the best data we have for the R process. But ideally, if I want to study a single origin for these elements, then I want to look for stars that are close to being primordial, if that makes sense. And I'll actually explain it more in a second. So that brings me back to the indirect observables on my silly little diagram here. These, what I'm calling indirect observables, are going to be stars that are chemically enhanced, that have elements that we can measure that appear in an R process pattern. And again, I'm going to take the next couple of slides just to explain what I mean by that. Okay, so specifically, stars that we call metal poor stars are as close as we can get to studying contributions by single events. So this plot shows the absolute abundances for the heavy elements in the solar system, sorry, for the R process component, and for just some random metal poor star. Now, just by looking at these absolute abundances, you can tell immediately that metal poor stars like this are chemically quite simple compared to the sun. In general, they have about 1,000 times less material, I should say less metals, less heavy element material than the solar system has. These don't have a lot of elements, I should say don't have high abundances of these elements. So these metal poor stars, again, are pretty close to being made of pristine primordial gas. There were very few generations of stellar evolution that preceded this star. You can kind of order of magnitude say, well, about 1,000 times fewer. And for that reason, these metal poor stars are often referred to as old, which is kind of accurate. So why these are noteworthy is because when we look at the elements that are actually in these metal poor stars, we're looking at records of some of the first generations of stellar evolution. So if these stars are that old, then there wasn't a lot that happened in the past that created those elements that we see in the stars. Now this plot is on an absolute abundance scale. If I plot that, all of those elements relative to their iron content, so that's what this little astronomer notation is, what I see is that for some of these stars, their heavy element patterns overlap with the solar system R process, which is really interesting because in these metal poor stars that don't have a lot of ancestors, these stars got most of their heavy elements, I should say, from what looks like just an R process event. And the solar line here is just the solar R process. If I were to plot the solar S plus R, it wouldn't agree with this metal poor star. So this is just showing that some stars, they show a pattern of heavy elements that looks like it's just from an R process. So there's another way of interpreting this plot, and that is if these patterns overlap, then you can kind of say that these elements, these heavy elements, are co-produced with iron. And for a while, that was one reason, well, among many reasons, why it was thought that core collapse supernovae were responsible for creating these elements, because they create a lot of iron too. And they saw this and said, well, it agrees, so clearly core collapse supernovae are producing this R process. However, more of these stars have been identified, and sometimes, actually somewhat often, they can have abundances of over 10 times the amount of the solar system R process. So if you take all of these heavy elements compared to their iron content, it's 10 to 100 times greater than what we see in the sun, again, compared to iron. So I hope that makes sense. What this means is when we, I call these stars highly enhanced. If they're highly enhanced in these elements, it means that those elements can't be made by the same thing that is making the iron. So it can't be supernovae. There's just too much of these heavy elements and comparatively not enough iron for something like supernovae to account for this. Okay, and just to kind of emphasize this again, because of their otherwise chemical simplicity, these stars are still metal poor, they're still old. They are considered some of the first descendants of the past R process events. And because they are metal poor, we can kind of assume that only one to a few R process events took place before these stars were made. So only a small handful actually went into making these elements, compared to the sun, who has who knows how many events that happened to pollute that gas. Okay, so this is a neutron star merger meeting after all. When am I going to get to the good stuff? What does this have to do with mergers? Well, there is observational support for rare prolific events like neutron star mergers to be the progenitors of these metal poor stars. And one of the most striking pieces of evidence for that is the stars identified in the Reticulum-2 ultra-faint dwarf galaxy, which is a satellite of the Milky Way about 30 kiloparsecs away. This image on the left just shows the sky in the direction of Reticulum-2, and the image on the right is the same portion of the sky, but it's only showing the stars that are a part of this dwarf galaxy. So calling these ultra-faint dwarf galaxies is very aptly named. These are very low mass, dark matter dominated galaxies. Okay, so in this galaxy, there were, well, not technically in this galaxy, but 2 independent studies looked at the abundances of 9 stars in this galaxy, 9 members of Reticulum-2. And what they found is that 7 of those 9 are considered heavily enhanced with these R process elements, which you can see by these red points belonging to this kind of upper branch here. And stars in other dwarf satellite galaxies of the Milky Way are not enhanced. They have lower amounts of this heavy element material. The other 2, by the way, I said 9 were studied, 7 of them are very highly enriched. The other 2 are just upper limits. So, they could be also very highly enhanced. Okay. So the question is, in this isolated galaxy that's very low mass, that doesn't, can't have too many energetic events going on because it'll just blow all the gas out. And plus these are very metal poor, so it doesn't have a lot of chemical evolution. What created this very, very enhanced signature? This is a lot of europium, a lot of heavy element material. If you assume these elements are co-produced with iron in a frequent but low yield site like Crocolaps supernovae, then the predicted yields you would get would be in this brown region, which clearly doesn't overlap with any data really at all. It overlaps with some of the upper limits, but it's not a good explanation for the stars in Reticulum-2. But if you assume a rare but prolific event like a neutron star merger, those yields are very consistent with the stars in Reticulum-2. And on top of that, this is one dwarf galaxy in this study, 10. So that's also indicating that this could be a very rare but prolific event. Which means, just to kind of summarize, when Reticulum-2 is still young, some R process nucleosynthesis event, like a merger, enriched this gas and then formed these stars. Okay, so just to, again, kind of summarize that, the identification of these stars in Reticulum-2 calls for specifically a high yield, rare event like a neutron star merger. And this was one of the most striking pieces of evidence that mergers are responsible for the heavy element patterns we see in similarly enriched stars, which then therefore means that these stars provide an elemental signature, a record that can be compared to neutron star merger simulations. Okay, so at this approximate halfway point, I hope I've convinced you that metal poor stars with enhancements in heavy elements could be these indirect signatures of neutron star mergers. There's observational evidence for a prolific but rare event like a merger. The next question is, well, if we assume that these stars came from mergers, can we learn something about mergers from the abundance patterns in the stars themselves? Or can we use that signature to say something about the merger or any of its properties, any of these really interesting physics questions? So before I continue the next half of this talk, I can say that it is complicated, it is very model dependent, but it can be done. And I'm going to show you one way in which we can learn about neutron star mergers from these stars. But I always have to think about this quote from Jurassic Park whenever I talk about this. You'll see that technically I can, but it's, again, very model dependent. One wonders if I should, if the constraints derived from these metal poor stars are meaningful enough given all of the other uncertainties. But this is a T-can meeting, not a T-should meeting. So with that caveat in mind, just bear with me. Why I think we can make these constraints is because elemental production depends sensitively on the astrophysics. And luckily this was talked about a little bit at the end of Jonas's talk. These plots are maybe a little complicated if you're not used to looking at them. They just show an overview of combinations of things like the neutron density and the temperature and the electron fraction and how those interplay to either give you a strong R process pattern or not. And as Jonas was saying, as what was in the chat as well, at very low YEs, things like entropy and, things like entropy and dynamical timescale don't really affect the pattern that much. It's the YE that's going to affect the pattern a lot. So with that in mind, again, the YE is one of the most sensitive parameters for the R process. Just to illustrate this, here are some simulations of neutron star merger tidal ejecta where I'm varying just that initial YE. So this blue line here is the output of a nucleosynthesis simulation I did, starting at this particular value of YE, which is going to change as I play this movie. So as this plays, there we go. As the YE decreases, it's becoming more neutron rich, you get heavier and heavier elements. That pattern kind of wiggles around. And I put this kind of as a last minute discussion point when Jonas said the pattern is robust at low enough YEs. I do want to come back and discuss that because it depends on how you define robust. But anyway, I'm going to play this again just so we can see at low YEs, high YEs, you're not producing a ton of these heavy elements, but as you crank up that neutron richness, you can get these very heavy elements, and then you don't get a lot of stuff over here. Okay. No, okay, now you're just stuck on a loop. Let me go to the next slide this way. Okay, so if we look at the abundances in the most R process enhanced stars, their patterns are shockingly similar. So each set of these points shows abundance patterns for 10 different R2, or sorry, I won't say R2 stars, 10 different R process enhanced stars. So each point set is one star. And for the most part, when you look at these abundances, they lie on top of each other every time. There's just no variation, and any variation at all can be easily accounted for in the observational uncertainties. However, there is some variation, especially in the actinides. This is a factor of 10 difference. That is outside of observational uncertainties. So this actinide difference is a signature of something else going on. Something is changing this R process, because at first people saw this consistency and thought, well, the R process happens the same way every time. And well, if you look at these variations and things like the actinides, maybe that's not exactly true. All right, now when I thought about these actinide abundances in the context of neutron star mergers, I thought about this YE parameter especially. Now I don't have to say this to this group at all, but different ejecta components in the merger can have different conditions like the YE, which can produce different abundance patterns. So this plot is a little bit of a simplification. It's just for demonstration purposes to show that very neutron-rich conditions, like what could be in the tidal ejecta from neutron star mergers, can produce very high levels of actinides. On the other hand, the wind ejecta or accretion disk outflows can be kind of neutron rich. That neutron richness depends on things like the hypermassive neutron star lifetime. This is something I would like to discuss if we have time as well. But that difference in the neutron richness affects the abundance pattern. It can produce a different set of abundances and maybe not produce the actinides as strongly as something like the tidal ejecta. Okay, so back to my observations here. I have Jeff Goldblum flashing in my mind again because I have these actinide variations. I have some type of at least explanation perhaps for where these variations could be coming from. If these stars have different merger progenitors, meaning it was a merger that created each of these abundance patterns, then the variation in these actinides could be indicating how much of the merger ejecta is tied up in that tidal tail and how much is tied up in the wind ejecta. Okay, oops, I did not mean for that to advance, I apologize. Okay, so there's a ton of simulation data out there, and I'm sure people in this meeting can very much attest to that. And a lot of simulation data out there can quantify how much mass is lost by either of these two components. And with all those simulation data, there have been a ton of groups, I'm sure there's more here, these are just the ones that come to mind, that have attempted to fit an analytic expression to those simulation data, to put this in a way that can be expressed with the neutron star masses themselves. So this is just an example, this plot here for the dynamical component. As the mass ratio is increased, I should say, as it becomes more asymmetric, you would expect a higher, more tidal deformations are going to release more mass. So you get more mass loss, the more asymmetric your system is. And again, I'm sorry if I offend anyone by that simplification. So what you can do is taking these equations and seeing that they both depend on the masses of the neutron stars. What I'm attempting to do, again, Jeff Goldblum flashing in my mind, is now can I use the predicted output from these neutron star merger simulations, compare those to my metal poor stars, compare those to their abundance patterns, and then ask for what masses of the merging neutron stars will those abundances match. So just to reword that to make more sense, since these masses for the dynamical ejecta and the wind ejecta depend on the masses of the neutron stars, I want to use the abundance patterns of metal poor stars to solve for M1 and M2, the original merging binary that could have produced these abundance patterns. And I do want to say, I know that this is equation of state dependent, very much so. So the results I'm going to show are under an equation of state assumption, unfortunately. Okay, and that's what is shown here. So what I've done, again, is I've taken the abundance patterns of metal poor stars for each star, asked which combination of M1 and M2 reproduces those abundances. So when I run my nucleosynthesis simulation, I convolve that with these predicted masses. I want those total abundance patterns to match my stars. And this is what I get. For stars, these metal poor stars that are considered non-enhanced or at very low enhancements, what I call like reconstructed binaries the reconstructed progenitor binaries for those stars tend to be pretty symmetric. They tend to be in this 1.3 to 1.4 solar mass range that looks like neutron stars that we see presently in the galaxy. However, for these very enhanced stars, like the ones in Reticulum 2, they would call for a progenitor binary that is slightly more massive and slightly more asymmetric than what we currently observe in the galaxy. So anyway, again, whether I can do this is, I mean, yes, obviously I can. If I should is another question. Point being, I have done it anyway. So these stars could be quite powerful, especially if we can hammer down some of the model uncertainties, since this is very model dependent. But you know, it can be done. We can use them to place some constraints on mergers. All right, so just to summarize, because I'm really at the end of my time here, and to bring this back, the direct observables, again, are just invaluable. However, observing things like kilonovae don't happen too often. On the other hand, we have these records, potential records of neutron star merger events having happened very far in the past through these R-process enhanced stars. And we have quite a few of them. We have more of these than we have kilonovae, but I guess it's easy to be greater than one, unfortunately. So my research and what I advocate for is including these as observables, because when it comes to these stars, we still aren't really sure where these stars came from. We aren't 100% sure that it is mergers. There's a lot about merger rates and other galactic chemical evolution things that need to be answered to account for these stars. However, they are still an observable that needs explaining. So neutron star merger models and their ejecta should not be in tension with the observations of these stars. And yes, it's another piece of the puzzle that makes this picture a little more complicated, but I'm trying to use them, therefore, as a separate tool for studying some of these same physics questions. And again, can I? Yes. Should I? We'll see. It is very model dependent. Okay, I'm going to leave the summary up, but first I just want to thank all my collaborators, and thank you again for listening to me talk about stars at a computational astrophysics meeting. And yeah, thank you for your attention.
Okay, so let's have first thank Erika for a nice talk, and then we have maybe time for a couple of questions before everyone takes a much needed break. Agnieszka, you're up.
Hello.
Hi.
Hi. Very nice, very interesting topic. I'm not expert in this observation, so I just want to have some more information on how do you actually observe those stars? Is it a spectroscopy methods? How intensive are the spectral lines which you probe, and how big error bars in the abundance values you can have?
Yeah, that's a great question. I usually put this series of slides in my talks, but I cut them out, and I'm very glad you asked this. Yes, we use high resolution spectroscopy. So that's, for anyone who's unfamiliar with that, you essentially are just splitting the light into its component wavelengths. And when you do that, this is a high resolution spectrum of the sun. When you do that, you see the light missing in certain areas. And of course, that corresponds to an atomic transition of an element, an atomic transition in an element or molecule that is present in that star's atmosphere. So each of those lines, yeah, corresponds to an element or a molecule. So that's what we do for these metal poor stars. Yeah, and as you asked, or as you kind of mentioned, because they're metal poor, they have very low abundances. Yes, the spectrum itself is a lot cleaner, but that means that these lines are also a lot less intense, I guess I should say. They're not as strong as in the sun, but we can still measure them. And here's an example. So here's some elements like, I don't know, strontium, barium, and europium. If you care about those, my favorites are the actinides, of course. I've said that a few times. So here's identification of thorium in a spectrum. We can get to some pretty low abundances if we have very high signal to noise and very high resolution. So this is a feature of uranium right here. And you can see this is a couple of % difference from if there was no uranium. So yeah, we can measure these pretty tiny features if we have good quality spectra.
They really look nice. And these stars, are they main sequence stars or evolved? How massive?
Yeah, that's a good question. Typically for the stars that have europium and these high R process enhancements, it's easier to do them on giant stars. And that's just because they are bright, they're very easy to identify. These, because of their temperatures, these lines appear deeper anyway. So they're just easier to measure in giant stars. The fact that they're giants doesn't necessarily interfere in these stars with these particular abundances. There are some corrections we need to make based on their evolution, but those corrections are more for things like carbon.
Okay, and maybe one more quick question if the Tzvi has his hand up. Tzvi?
Yeah, it's not a question, it's actually a quick comment. You don't have to go that far away to realize that our process elements are produced in rare events. Even our own solar system gives indication about that. Early measurements of plutonium abundance, radioactive plutonium abundance from meteorites indicate that around the time that the solar system was born, less than 100 million years before the solar system was born, there was excess of production of our process elements near the solar system by about a factor of 1,000 larger than the abundance of surrounding our process element in the vicinity of the solar system now. So just this very single fact from our own solar system tell us that these rare elements are produced in rare events and not in a standard supernova.
Yes, yeah, thank you for bringing that up. I completely neglected to talk about meteorites. Yeah, thank you.
Okay, well, thank you to all the speakers in this session. It's time for a break.